Organic Chemistry 212, Exam 1 Material Part 2. Just as a reminder, I highly recommend that you go ahead and read the textbook first before you go through these videos. That way the material doesn't seem like a surprise to you, and hopefully these videos clear up information you weren't sure of and can fill in some gaps that you might have. So if you haven't already read the textbook on this information, please go back to your textbook, read it, and then come on back and fill in your lecture notes. All right, polar covalent bonds, acids and bases. So again, this is chapter 2 material in the McMurray textbook, and usually this information is skipped by a lot of OCHEM instructors because this is the same material that you learn in general chemistry, so it's a review of the material. So if you have any questions on some of this information, if I don't go into it in depth enough, be sure to look back on your Gen Chem text or go ahead and Google the topic and you can look at some tutorials and reviews on that. Polar covalent bonds. Polar covalent bonds can have some ionic character, and these are known as polar covalent bonds. And this happens when you have two atoms of a different electronegativity bonded to each other covalently. Now, if they have such a big difference in electronegativity, they actually become ionic bond, where one grabs the whole electron from the other guy and you get a positive and negative happening. What we're also looking at here are the instances where it doesn't completely take the electrons, where it's sharing it unequally. So different atoms have a different electronegativity. So for example, if you have one of the halogens that are high electronegative, it's not going to share the electron cloud equally with a carbon or an element that is less electronegative. So taking a look at that, look at the electron distribution between atoms, it's not necessarily symmetrical. Now, it is symmetrical when they have very close electronegativity. So the cloud is equal, and we're not going to have any polar or any slight positive or negative charge happening. But as soon as we get one atom that has more electronegativity, in this case they're showing us this Y is more electronegative, it's going to pull the electron cloud more towards it. So this part of the molecule itself will have a slight negative charge, and the other side that has a less electron density will have a slight positive charge. So these symbols here are commonly used to show polarity with organic compounds. This symbol here is the lowercase Greek letter delta. So this is a delta. It's almost like a lowercase d that's been kind of swirly quite a bit. And it's showing me that it has a bit of positive character on this atom specifically, whereas this one labeled Y has more negative character to it. So that means this molecule itself is a polar molecule. It has a positive end and a negative end. Now the molecule itself carries no overall charge. It's just one end is more negative and one is more positive. This happens a lot with organic compounds, and it's also, we need to know about this because if we want to react it, if something is positively charged, it's going to be attracted to this end. If something that comes in that's negatively charged, it'll be attracted to this end. Now the one that's symmetrical covalent bond is not going to be attracted anywhere. It's not going to do anything. We don't have any negative or positive to entice it to come in here. But a polar covalent bond can do that. So we need to keep that in mind. Part of the physical properties here on looking at the polarity is going to help us understand reactions later on. And if you have a big enough difference, as you learned in Gen Chem, between the two atoms themselves, one can completely take the electrons, causing it to be negatively charged and leaving a cation behind. Here's a periodic table of electronegativity, keeping in mind fluorine is the highest electronegative at 4. Carbon is at about 2.5, and I know hydrogen's at 2.1. Basically, they don't consider that being a big enough difference between carbon and hydrogen to cause any polarity, so you're not going to see polarity between carbon and hydrogen. The other elements that we commonly see with carbon are going to be your nitrogen, oxygen, fluorine, chlorine, and bromine, and so there's going to be slight polarity happening on with those, and pretty much a lot of polarity happening on with fluorine right there. So we can use electronegativity to help determine what kind of bond type we're going to have. If you have a difference of about less than 0.3, it's going to be covalent. It's going to share the electron cloud pretty much equally. A polar covalent bond is usually the range of about 0.3 to 2, and ionic bond is typically greater than 2. So we previously talked about this delta, lowercase delta, and I've got it written up here. And typically when you're typing it up or writing it, it's typically shown as a superscript, but sometimes it's just too small to do that, so they'll go ahead and write it like this. But typically it's more written like this. We use the delta symbol to indicate polarity. Again, the positive is the positive charge, negative charge. So we have a chlorine here. I'm sorry, there's my chlorine. Chlorine attached to a carbon right here. And we know chlorine's more electronegative than carbon. So chlorine would have the delta negative next to its atom. Be careful that you don't write it too close to the carbon because we don't want to be mistaken. And then the carbon would have a slight positive charge. So what this means is if we are trying to do a reaction, what happens is if something is negatively charged, it's going to want to attack this carbon site. If something is positively charged, it'll want to attack the chlorine site. So we're going to have different areas of our molecule that are going to be attracting different kinds of things. Now, we've got this picture on the side, and for some reason McMurray thought this was quite helpful. So it's showing you the electronegativity in red, and this is actually showing you electropositive, more electronegative down here. These rainbow pictures, don't really worry about them. They just happen to add them. But the new piece here that I want to talk about, remember we talked about deltas before, difference in electronegativity. Well, we can also describe the same concept with a different term. So we're not changing the concept. We know that chlorine has more electron cloud than carbon. What we can do is we can also show it in what's called dipole moment. And dipole moment has the Greek letter mu as its symbol, but the way you use it is you have an arrow, and the arrow goes towards where the electrons are being pulled, and the tail end of it gets what looks like a positive charge. So let's see how we use it here. We have carbon that is slightly positively charged. So you'd start the arrow here, and you would draw it towards the more electronegative element, in this case the chlorine atom. And notice it's showing me that the electrons are being pulled this way. So it's a little more descriptive, it's more illustrative. And the tail end of it gets the positive charge. So you can see this end, carbon, is more positively charged, and electrons are being pulled this way. So you will see both of these being used at different times, or sometimes they might ask you to draw them both. So how do you know which one to use? If I ask you to show me polarity, I want you to show me the delta symbols. If I ask you to show dipole moment, you use this arrow symbol. And a lot of times I'll actually ask you to use both, so be prepared to use both and know the difference. So what your textbook has is an interesting example here where we have carbon with something that is actually less electronegative, and that's lithium. If you know where lithium is on the periodic table, is on the left-hand side, and electronegativity trend increases as we go across from left to right on the periodic table. So here's an interesting thing. Lithium has a positive charge, or partial positive charge, while in this case my carbon has a negative charge. So then the dipole moment, it always has the one that's more, has the positive charge, and the arrows are always going to the one that's more electronegative, showing me where the electrons are being pulled to. So this is showing me the difference on how to represent the same concept. Electrons being pulled more towards one element than another. Sometimes we want to see it in terms of polarity. Sometimes we want to see it in terms of dipole moment. Next, we're going to talk about formal charges. And you've seen formal charges before when you worked with polyatomic ions. Let's take a look at this. If we have something with a formal charge, now this isn't the same as polarity. Polarity was a partial charge on one end of the molecule that's counterbalanced with the opposite charge on the other end of the molecule, and the whole molecule itself is not charged. We are now talking about the situation when we actually have something that has a charge on it, either positive charge or negative charge or a combination of that. So we're talking about full charges here. So formal charge, specific atoms in a molecule can be assigned a formal charge. The formal charge can be used to help select which Lewis structure is most stable. An overall charge of 0 is best. So if we have competing Lewis structures, the one that's most stable is the one with no charge at all. The negative charge on the more electronegative element is also more stable. Now remember, 0 charge is the best. So how do you determine formal charges on an organic compound? Well, your textbook has a really long calculation that you have to do, and I wrote the summary here. The formal charge is equal to the number of electrons minus the number of bonding electrons divided by 2 minus the number of non-bonding electrons. That's great. That works all the time. But I actually want to show you a shortcut. Let's look at the next slide. Oh, not a shortcut yet. Sorry, this is out of your textbook. This is how we can look at formal charges. That's the same formula there as we had on the previous slide. You can go through this on the textbook. Take a look at this. I have Carbon single bonded to hydrogens here, 1, 2, 3. Nitrogen double bonded oxygen here, single bonded here. Remember, oxygen doesn't have enough bonds right here. How many bonds is oxygen supposed to have? It's supposed to have 2, and notice he doesn't have enough bonds. Nitrogen, what's his preferred number of bonds? This was a few slides back. In fact, on the previous set of slides, it's supposed to have 3, and notice it has 1, 2, 3, 4. So that's kind of messed up. That's where the formal charges come in. If something has the preferred number of bonds, it doesn't have a formal charge. It's when the atom itself has a differing number of bonds than that preferred number of bonds. So let's take a look. I mean, if you want to go ahead and go through this, go ahead and do this. This works every time, but I actually have a shortcut that works about 90–95% of the time, and so I want to show you this one. Okay, here's my shortcut. On most atoms, formal charge can be found by a shortcut. Now, the previous slide, you can do formal charges for everything, but most of the time, the shortcut's going to work for you. What you have to keep in mind is preferred number of bonds. So let's take a look at here. If it has the right number of bonds, there's no charge there. So carbon needs 4 bonds total. This one has 4, so there's no charge on this carbon at all. No formal charge. This carbon, how many bonds does it have? 1, 2, 3, 4. So there's no formal charge on that one either. Oxygen, what's preferred number of bonds? 2. 1, 2, it has 2. Now this oxygen here, he doesn't have all the bonds it's supposed to. It only has 1 bond. Oxygen has 2 preferred bonds, right? It's supposed to have 2 bonds. How many bonds does this one have? 1. So isn't it missing 1 bond? That's its formal charge. Take a look at this. This is a great shortcut. I know it went kind of quick, but we'll practice this a lot. If you look at how many preferred bonds it has, and if it has less than what it's supposed to, you write down minus and how many bonds it's missing. Now, this example here in the middle, so this molecule has a formal charge of -1 overall. Now, this is the example they had on the previous slide where they went through a whole bunch of work to do this. Let me show you this. Carbon here has 4 bonds, so it has no formal charge. Nitrogen has 1, 2, 3, 4 bonds. Did you notice it has 1 more bond than preferred? Remember, the preferred number of bonds for nitrogen is 3. So it's supposed to have 3, and it has 1 more than it's supposed to. So its formal charge would be a +1. Let's check this again. Nitrogen is supposed to have 3 bonds. It has 1, 2, 3, 4. It has +1 more than it's supposed to. So the formal charge on this nitrogen is +1. This oxygen has 2 bonds, so it doesn't have a charge because it's what it's supposed to be. But this oxygen here has only 1 bond. It's supposed to have 2. It's missing a bond, -1. These are the formal charges. Go back and look at the page we had before. They will tell you that this oxygen's a -1 and this nitrogen is a +1. Well, I've got to tell you, this is a lot easier than doing that other calculation over there. And talking about stability, this has a +1, -1. It's neutral, so it has an overall 0. So this is a very stable molecule. Whereas the one previous right here, it has a -1 charge. It's not going to be as stable. All right, so what I want you to do is, you're going to pause the video in just a minute here. I want you to count how many preferred bonds, and I want you to assign formal charges to all these different molecules. Come on back and check your work. All right, so this carbon, he has the appropriate number of bonds, so he doesn't have a charge. Nitrogen has 1, 2, 3, 4. It's supposed to have 3, so it has a +1 charge. This carbon has 1, 2, 3 bonds. It needs 1 more, so it's lacking a bond, so it's a -1. This nitrogen has 3. This carbon has 4. Those are okay. This guy's lacking 2, so it'd be a -2 charge. This oxygen is lacking a bond, -1. This nitrogen has 1, 2, 3, 4 bonds, 1 more than it's supposed to. And this one has, sulfur has 1, 2, 3, 4 bonds. It's supposed to have 2, so it has a +2 charge. How'd you do? So we saw on the previous slides formal charges, and we saw that in some of those cases, this is actually the same molecule we've been working at already. See how this has a plus charge and this has a minus charge? These are the formal charges. And what we're looking at here is, if you notice that we had the carbon double bonded, didn't have a charge, but we had a carbon with a single bond. Well, what happens is it doesn't stay like this. What happens, it's known as resonance, and that's when the electrons move around, because this oxygen up here that has the 2 bonds, Why doesn't this one also have two bonds? Well, it doesn't think it's fair. So what really happens is we get movement of electrons. So what's going to happen is called resonance. Resonance is when the electrons themselves move around, the atoms stay put to make the molecule more stable. So what's going to happen is take a look, first of all, at this arrow right here. This arrow is a single line with a double head on it, an arrowhead on each side. This is supposed to be used for resonance. Sometimes people use this incorrectly when they were doing equilibrium, and that was back in general chemistry. Equilibrium are supposed to be two separate arrows. Well, a resonance arrow is supposed to be a single line with an arrowhead on each side. So for this class, you are responsible to use the correct arrow. What resonance means is my atoms are staying put, and let's take a look at the difference between the molecule on the left and on the right. In this case, this oxygen has a double bond and no formal charge. Well, in this case, it lost the double bond, and what happens is it now has a negative charge, while this guy has the double bond and no charge. So what's going to happen is that the pair of electrons is going to fly back and forth between these two oxygens so fast, and so to go back and forth, that it's going to become more stable by being a resonance of this one and this one. So which one is existing? They both exist, because if you can imagine how fast those electrons move at any one moment, as soon as we say, remember Heisenberg uncertainty principle, as soon as we say the electron is here, it's moved back and forth millions of times. It's going so fast. So both of them are correct. So here's the thing that's interesting about resonance structures. The more resonance structures you have, the more stable the molecule. So this molecule not only does it have a plus charge and a minus charge, which is neutral, we talked about that earlier, it's a zero charge overall. Well, what happens is because it has its resonance structure, it goes back and forth so quickly that it's extremely stable. So which of these Lewis structures are correct? They're actually both correct. So how do we determine resonance structures? Here's some rules or guidelines to help you figure that out. Rule 1, individual resonance forms are imaginary. The real structure is a hybrid of the different forms. Rule 2, resonance forms differ only in the placement of pi or non-bonding electrons. Those sigma bonds never, ever, ever move. That's why the atoms stay put. Remember, the first bond that always holds two atoms together is the sigma. Sigma bonds are not involved in resonance at all. It is only either lone pairs or pi electrons that are involved in this. Rule 3, different resonance forms don't have to be equal. Rule 4, resonance structure must be valid Lewis structures. They have to follow the octet rule. And rule 5, the resonance hybrid is more stable than individual resonance forms. One of the most popular, or one of the big ones in organic chemistry, happens to be benzene. And benzene right here, sometimes you'll see benzene written with the circle in here as opposed to the alternating double bonds. And that's what's happening here. You have carbon, double bond, carbon, single bond, double bond, single bond. You see the alternating double bonds? Well, what happens in benzene is the electrons that are here right now, let's point right here, they're actually going to go next door. One of the things that happens when you have double bonds is double bonds don't live next door to each other. For example, you can't have a double bond next to a double bond on another carbon. So as soon as this double bond goes here, this guy doesn't like it. These electrons say, hey, I'm not sticking around. You're kind of encroaching on my area. So this paired double bond will go here, and so on. So it keeps going around and around, and it goes so fast. You have two resonance forms that at any one time, they're going so fast. What they'll do for benzene specifically is they'll show the electrons as a circle, and that's showing the resonance piece of that, or the aromatic piece of that. We'll get into benzene more next semester, but I wanted you to see that because most likely taking OCHEM, you've already seen this structure before. So benzene has two resonance forms. It's especially stable. You can show benzene with the alternating double bonds, or you can show it with the ring. Here's another example of resonance. Here we have three atoms. We have a double bond between what they have is X and Y, and a single bond here is Z. So you can kind of see it drawn here, but you see the lobes here. And what happens is these pair of electrons here cannot tell the difference. The ones, remember the pi electrons, it sees this pi orbital over here. So this pi electrons here, remember the sigma stay put, the pi electrons say, hey, what if we went over here? And that's what's happening here. All of a sudden the electrons are over here. and then they're impatient or something like that, and they say, oh, we have an open pi orbital over here. Let's go over here instead. So that comes back over to here. And that's what happens in resonances. The pi electrons, in this case, are going back and forth between the pi orbitals. So it is a resonance between the two. Now, if you're drawing the Lewis dot structure, you will draw one or the other. If you're asked to draw the resonance, you must draw both. So here's a common example. I know I told you benzene's a common example. For a linear compound or non-cyclic, this 2,4-pentane dione is a really common example. Most textbooks use this. You find this on standardized tests a whole bunch. So it's a really good structure to get an idea of what's going on for resonance. Do you notice the resonance arrow here? And I have another one here. That means 2,4-pentane dione has 3 resonance structures. The more resonance structures you have, the more stable the molecule. So this is an especially stable molecule. Let's take a look at the beginning here. We have oxygen with 2 bonds, so that's okay. It doesn't have a charge. We have carbon with 4 here, carbon with 4 here. This carbon has a lone pair and a negative charge. That's what this is. Do you see the 2 dots and the minus charge? That means carbon, he has to have his octet. So he does have his octet, 2, 4, 6, 8. But he has a negative charge. So he's called a carb anion is actually what he's called. And because he only has 1, 2, 3 bonds, he has a formal charge of a negative. That's where the negative here came from. And then we have carbon with 4 bonds, oxygen 2, and this carbon's fine. So the only thing that's really not working well is this carbon here has a negative charge. Well, one of the things we have to keep in mind when we talked about stability of resonance structures is the more electronegative element is more stable if it has a negative charge. And this oxygen is more electronegative. So carbon really doesn't want to have this negative charge. Oxygen's saying, hey, I can handle a negative charge. I'm more electronegative. Why don't you give it to me? So let's see what happens. It's not the negative charge that's going over here. It's actually the pair of electrons. These pair of electrons are now going to be bonded between these 2 carbons. So let's go over here for just a second. Ignore the arrows for just a minute. Do you see that this carbon and this carbon have no longer a single bond, they have a double bond. Now, once these electrons go here and form a double bond, do you see how this carbon has too many bonds now? It'd be 2, 3, 4, 5. It has way too many bonds, too many electrons. Octet is way too much. So it's going to force one of the pair of electrons. Remember, a double bond is 2 pairs of electrons. So 1 pair of electrons is going to go up to this oxygen here. And what it does is it makes a single bond to carbon with 2, 4, 6, 8 electrons. It only has 1 bond, so it has a negative charge now. So what happens is during this resonance piece is the pair of electrons form a carbon-carbon double bond here, and at the same time a pair of these electrons come up here to make this have the negative charge, my oxygen. And oxygen would much rather have the negative charge than the carbon. So if I were to compare just these 2 resonance structures, which one would be more stable? If you pick this one, you're correct because it's the oxygen that's more electronegative with the negative charge. This one would be more stable. That means this one, the one that's more stable, it's in that form longer. It's more stable. All right, so what else can happen? It has 3 resonance structures. So now let's look at the arrows here. One of the things with organic chemistry is whenever you have a curved arrow, so you saw curved arrows here and here, is whenever you have a curved arrow, that's telling you that electrons are being moved. And this has a normal arrowhead. Notice it has both sides of the arrowhead. So that means 2 electrons are being moved. So a pair of electrons from here is going to come down here to form a double bond between this oxygen and this carbon. That means the formal charge is going to go away. So let's look over here. Do you see how after this pair of electrons forms a carbon-oxygen double bond that this no longer has a charge? It still has its octet and it has 2 bonds. But as soon as this pair of electrons come here and causes an oxygen-carbon double bond, that's too many electrons and too many bonds to carbon. So this carbon-carbon double bond, a pair of electrons are going to come over here. And then it's even going to cause another thing to happen because we have our double bond. It's going to cause another pair of electrons to come up to here. So let's look at the result. We started here. This is where it all started. This is the tail end of the first arrow. Causes a pair of electrons to go here. Then we have a pair of electrons to go here and a pair of electrons go here. That means this will have no charge. I will have a double bond between here and here. I'll no longer have a double bond between here and here. I'll have a double bond over here. See how that is? And then this one will have the negative charge. All right, comparing stabilities. Do you see this has an oxygen with a negative charge, and this is an oxygen with a negative charge? This resonance structure, the third one written, the one in the middle, they actually have, they're identical in energy to each other. They would both be the same stability. But this one over here, the first one written, would be lower. It would not be as stable at all. One of the key points is when we move electrons, we can have charges change. We can have multiple bonds formed or taken away. And in resonance terms, the more resonance structures we have, the more stable the molecule. All right, so I told you a little bit about curved arrows on the previous slide. Here, your textbook finally actually gets to the arrows. So let's take a look at this. Curved arrows and resonance forms. So here we have the same structure here. See, the pair of electrons are curved arrows going here. So we're going to have a double bond there. And a pair of these electrons are going to come down here. So the curved arrows tell us the movement of electrons. And this is the beginning of one of the things we're going to be doing called mechanisms. We're going to show how the electrons are moving, and that helps us understand how reactions happen and stuff like this. So we can imagine that the electrons move in pairs. And again, I want you to notice that the arrowhead here is a full arrowhead. That means 2 electrons are moving. We're actually going to have later on a single electron move. So let me show you something. All right, right now we're seeing arrowheads with the normal double arrowhead here. And I know mine's not drawn so good here, but this would be a double arrowhead. Then when you have a normal arrowhead with the 2 sides being shown here, you have 2 electrons that are being moved, 2 electrons. When you have what's called a fish hook, so it'd only be half of the arrowhead happening, only 1/2 of it, then only 1 electron is moving. So right now we're seeing a pair of electrons, and I know it's a pair of electrons because the arrow has the full arrowhead on it. It's not 1 electron, it's a pair. So we can imagine electrons move in pairs to convert from one resonance form to another. A curved arrow shows that a pair of electrons moves from one atom or bond at the tail end to the arrow, and using the arrow to go to what atom or bond. So take a look at this. We have a pair of electrons going to the bond here. It's not going to nitrogen, it's going to the bond. So you have to be careful that the arrow goes to the bond and not to another atom. Whereas this pair of electrons is actually going to the atom oxygen, and that's why it's pointing to oxygen. So you have to be very intentional when you do this. If the electrons are going to a bond, draw it to a bond. If the electrons are going to an atom, draw it to the atom. So at this point, I want you to go ahead and you're going to pause the video in just a second, but I want you to draw on this one what arrows you would have to look like this one over here. I want you to draw the electron, the curved arrows showing what's going on. Now, keep in mind, the tail end here is where it's all starting. Where is it starting? It's going here, and because of that, this is going here, kind of a domino effect. So be careful when you do this. Make sure you take a look at what the before and after picture. I want you to notice that up here we have a single bond versus a double bond oxygen, and down here this one's double and this one's single. So keep all those pieces in mind. So go ahead and draw the curved arrows on this molecule here that would cause the resonance structure on the left of it. Come back and see how you did. Okay, in this case, this oxygen becomes double bonded. So a pair of electrons, I'm going to go ahead and grab this one right here. A pair of electrons are going to specifically go to this bond right here. Remember, it's not the negative charge that's doing it, it's a pair of electrons that's doing that. So I went ahead and let this pair of electrons, by a curved arrow, I'm showing that it's going here. Let me make my arrowhead a little bit more. You can see it's 2 electrons going here. So I have no charge once these electrons go in a carbon-carbon double, or I'm sorry, carbon oxygen-nitrogen bond here. Now, right, and what's going to happen is nitrogen has a double bond oxygen here, and it's not going to like it. It wants a single bond. So what's going to happen is a pair of electrons here is going to go to this oxygen specifically, and it's going to end up having 6 total and become a formal charge of negative. How'd you do? Bronsted-Lowry acid and bases. The definition, the Bronsted-Lowry definition of an acid and base is an acid is a proton donor and a base is a proton acceptor. So what we're doing is we're looking at our organic compounds now in terms of what's going to donate a proton and what's going to accept the proton. So taking a look at my first structure here, this happens to be an acid. In fact, it's acetic acid. You probably use this in general chemistry quite a bit. And we have this hydrogen right here that I have in red is the acidic proton, the acidic hydrogen, the one that's able to leave. What makes something an acid is its ability to give up a hydrogen, and it's this one that can leave. Now we have 3 more hydrogens on here, but they're bonded to carbon. And if you keep in mind, these are very similar in electronegativity, so they don't have a polar bond going on. But we do have a polar bond going on between this hydrogen and this oxygen. And on top of that, we have another oxygen double bonded, so all the electrons are being pulled in this direction away from this hydrogen. So this hydrogen is loosely held. And so that means something can come around and take it. So what can come around in an acid-base reaction is a base. So I have an OH minus here, and what's going to happen is this OH is going to come close to this hydrogen and it's going to grab it. And that's where we get this HOH piece that comes off of that. And because this oxygen is missing a hydrogen, it has a negative charge. So this oxygen is going to get a formal charge of -1, and that's where this minus comes from. Remember the formal charges? It's supposed to have 2 bonds, it has 1, and so it gets a minus charge. During an acid-base reaction, our acid reacts with the base, and our acid, when it loses its hydrogen, becomes a conjugate base, and our base becomes a conjugate acid. One of the things we can get from this is we can look at the acidity constant, Ka, and also the dissociation reaction. So this right here is Ha. This is a general acid with the hydrogen. You know, we write the hydrogen in the front generally when we look at acids. So H is the hydrogen, A is the anion that's with it, and water. And we see we have here in the dissociation reaction, in this case, we have an equal arrow. This is that equilibrium arrow that's supposed to be 2 separate arrows. So do not use the resonance arrow here. You can't use a single line with the 2 arrowheads, that's resonance. You must use 2 separate arrows. And because they're both the same distance, that means it's in equilibrium. It's just as likely to go in the forward direction as the reverse direction. So in this acid-base reaction, this acid loses its hydrogen, becomes an anion. And what happens is water grabs that hydrogen and it becomes the hydronium ion with the positive charge. So this reaction I have across here is the dissociation reaction. Beneath it in the square is what's called the equilibrium expression. And the equilibrium expression, Ka, is equal to, it's always the concentration of the products over the concentration of the reactants. Do not include solids or water. So notice I have water here, so I'm not going to include water on the bottom. And anytime you put a symbol inside of a bracket like this, in the equilibrium constant, that's telling us it's the concentration of. And because I have an understood coefficient of 1 on all of these, I don't have any superscripts up here. And also remember, it's taking these two, in this case, this one and this one, they're multiplying each other here. So please do not put a plus sign in here. There's a plus sign in the reaction, but in the equilibrium expression, it's the concentration of the hydronium times the concentration of the anion. You will be responsible to be able to take a look at an organic reaction, write out its dissociation reaction, which would be the top piece, and also write its corresponding equilibrium expression. So here's kind of a neat thing that I do with my OCHEM students is you've done a whole bunch of equilibrium expressions and dissociation reactions in Gen Chem where you've had to fill in the concentrations and calculate all that stuff. Well, for this class, you're not going to have to calculate any of them. You're going to have to set up the dissociation reaction and the equilibrium expression, but you're not going to have to actually calculate it. Good news, huh? One of the things we can get from the Ka is we can predict whether or not we're going to have a strong or weak acid. So that's the piece that you need to know, the theory piece behind this. So not only do you need to be able to write down the dissociation reaction and corresponding equilibrium expression, you have to be able to look at it and get an idea if it's going to be a strong or weak acid and compare them. So for example, if you were given a table of pKa's or Ka's, you should be able to tell me which one is stronger or weaker. So let's take a look at how this works. Acid strength expressed as pKa. pKa is minus the log of the Ka. So you saw on the previous slide how we got Ka. Well, those numbers are something not quite manageable, or we're not really comfortable with them. They'd be times 10 to the minus 7, times 10 to the minus 12, those kind of numbers. So anytime you take minus the log of a number, we're converting those exponents to a number that's more easily read. So you've seen this done before when we did pHs. If you remember, a pH is minus the log of the H concentration. So anytime in chemistry we see a lowercase p in front of a symbol, we know that they took the number and manipulated it by taking minus the log of that. And those numbers are just, like I said, easier for us to look at, like pHs and such. So the theory part that you need to know. A strong acid, an acid that's really willing to give up his hydrogen, will have a small pKa. A strong acid will also have a large Ka. A weak acid, so this is an acid that's not really as likely to give up his hydrogen, he will have a large pKa and a small Ka. So you need to know the theory behind this so you can compare them. So you can predict if an acid-base reaction will occur from the pKa. An acid with a lower pKa will react with the conjugate base of an acid with a higher pKa. So again, this is all the theory stuff that you learned back from Gen Chem. If this isn't enough explanation, please go back to your Gen Chem book, or again, you can Google the information and get a better idea of how to look at that. Remember, you're not actually calculating. You need to know the theory and how to compare if you were given a table of numbers. Now we're going to look at the Lewis acid and base definition. In the Lewis acid and base definition, an acid accepts an electron pair, whereas a base donates an electron pair. So take a look at this. We have a filled orbital. A base here has the electron pair right here, donates the pair, while the acid has the vacant orbital. So what's going to happen is this base is going to give the 2 electrons. Well, actually, it's going to share the electrons. It's not going to give the electrons. It's going to share the electrons, and now they'll have a covalent bond together. And that's what we see with OCHEM. So, we have some arrows here. Let's see what's happening. Now, when you have arrows, you always look at the tail end to see where it's starting. So let's see what's happening here. We have a pair of electrons that are going to be transferred over to the hydrogen specifically. And then we have between my HCl, I know it's written kind of backwards. You're used to it being HCl, but this is still HCl. The pair of electrons, see how it's the pair of electrons in the bond, see how it's at the bond itself, is going to go to the chloride, and that's going to make a negative charge, and that's what's going to happen here. So when you're starting off here, this pair of electrons is going to covalently bond to this hydrogen. That's what happened here. And then the pair of electrons that are holding these two guys together, because remember, hydrogen can never have more than one bond. It's going to covalently bond here. Well, what's going to happen is the pair of electrons are going to go here and make a chloride. Well, we know chlorine loves to have a negative charge. We've seen that with ionic stuff before. So what is the net result? I now have my hydronium ion being formed. The oxygen on the lone pair of electrons on my oxygen are going to physically bond to this hydrogen. Hydrogen can't have more than 2 bonds, so the pair of electrons that was holding together is going to go to the chloride. So this is an example of what happens during an acid-base reaction. Notice I have my equilibrium arrows here. I have 2 arrows the same distance. In this case, they're showing you it's just as likely to go in the forward direction as the reverse direction. So not only am I showing you curved arrows on where the electrons are going, but I also have some charges, formal charges going on. The preferred number of bonds for oxygen is 2. Notice it has a plus charge because it has 1 more bond than it's supposed to. And the hydronium ion, H3O+, that's where the plus comes from here, the formal charge of oxygen. And then chloride has 1 less bond. Remember, it can only have 1 bond. It has none, so it has the negative charge. So looking at charges in terms of formal charges, not just as ions. Okay, so this piece came up after I talked to you. Here we go. Curved arrows show the movement of electrons. We have a pair of electrons here, another pair here. Organic acids and bases. There are 2 main kinds of organic acids. Those that contain an HO bond, and another type of acid that contains a hydrogen on a carbon next to a C double bond O. This is called a carbonyl group. So let me show you some examples. Here is an HO bond right here. I know I wrote HO, but here's OH in the opposite direction. So when this hydrogen is bonded to this oxygen, remember the oxygen is more electronegative, and so the electron cloud is going to be pulled more towards it. So it'll be more, in this case, we'd have a delta negative here with a delta positive here. That means this hydrogen's not being held on real tightly because we have a polar covalent bond, meaning something can come around and take this hydrogen. What makes something an acid is its ability to give up a hydrogen. Now, this may not be a very strong acid. I mean, it's an alcohol. It may not be a very strong acid, but it does have the potential of becoming an acid by losing that hydrogen here. Now again, as we saw before, these three hydrogens are not bonded to something more electronegative, so these are not going to be polar at all. So these aren't involved in any way. Well, not only do we have C double bond O in this case, but we also have this oxygen here. This is that acetic acid we saw earlier. So this hydrogen here is really not held on very tightly because not only are the electron clouds being pulled more towards this oxygen, it's also being pulled in this direction. So this hydrogen is very loosely held. So this hydrogen is the acidic hydrogen ready to go. Now, we also have some acidity on, do you see here it says CH next to C double bond O? So this carbon right here is what we're talking about in this case here. And these hydrogens, they're not held on as tightly if we didn't have this. What's happening is this double bond O is pulling some of the electron cloud this way and this way. So this hydrogen here has the potential to act as an acid and leave. But again, in acid strength, something that's very, very likely to give up its hydrogen, like HCl is a strong acid, versus this acetone is a very, very weak acid. It's not likely to give up this hydrogen. In fact, most likely there's going to be reactions happening in other places on the molecule before that. But we do need to know that this does have the potential to be acidic. So let's look back at our acidic acid here. We have that same situation. Notice carbon double bond O CH3, carbon double bond O CH3. So yes, these hydrogens are slightly acidic, but this one is so much more that this one's gone long before these guys can even think about leaving. So when we talk about the acidic hydrogen and acidic acid, it's only this one here because that one's going to leave much, much sooner than these guys can ever do it. Organic bases, typically we're looking at bases that contain nitrogen because remember bases are going to be accepting the hydrogen. And nitrogen prefers to have 3 bonds, but we do know that it can have 4 bonds. Do you guys remember the ammonium ion, NH4+? Well, what's going to happen is nitrogen prefers 3 bonds, but he can have 4. In this case, he has 3 bonds. And what's going to happen is this hydrogen here is going to bond to this nitrogen here. And do you see how I now have 3 hydrogens? The CH3 is still there. So what's going to happen is nitrogen has 4 bonds. It has 1 more bond than it's supposed to, so it gets a plus charge. And chloride is going to be an anion. He's going to get a negative charge. So this is an example of an organic base containing nitrogen and a lone pair. The nitrogen is going to grab the hydrogen. Lone pair is gone, but it becomes a plus charge on our nitrogen. Drawing chemical structures. So we want to know what the structure looks like because if we have a molecular formula, the molecular formula could have different isomers, and isomers is when you have the same molecular formula but a different structure. Don't confuse that with isotopes that we talked about earlier. That is actually something different. So we're looking at, we're talking about different structures that are possible. So we do want to know the structure of something. So a molecular formula. So a molecular formula, take a look at this. This has 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. So that would be C5. How many hydrogens? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. So what I have written off to the side here, C5H12, that's a molecular formula. It is not the same as a structural formula. In fact, C5H12 could have different structures than this one. This is just one of the isomers of it that I'm showing you. So most of the time when I ask you to draw a structural formula, what I need you to do is actually draw what's known as a condensed structural, because do you see how much space this one takes up? Explicitly showing the hydrogens. And what I had to do is exaggerate the bond here so these hydrogens don't actually get on top of those to make it clear. So what happens is sometimes we need to show explicitly the hydrogens, and maybe we show them to talk about different parts of the molecule. But I want you to notice this is 2-methylbutane. So where'd the butane come from? Right here. But is where we have 4 carbons A and E tells me single bonded. So do you see I have 1, 2, 3, 4 carbons in a row? Here's 4 carbons, that's the bute part, and they're all single bonded, so that's the butane. Now coming off carbon number 2, don't forget we can also read this in this direction. This could be carbon number 1, carbon number 2, carbon number 3, carbon number 4. Remember, in English we read from left to right, but this molecule, it's not going to be necessarily left to right. It's three-dimensional. It's floating in space. It could be upside down, flipped around. You look for the branch and you go from the end that is shortest. It gets the shortest number. So going in this direction, I have a branch coming off carbon number 2. If I were going from this direction, it would be 3. 2 wins. When we get to nomenclature, you'll see this some more. So if you don't get it right now, don't worry. We'll definitely cover this again. But do you notice on carbon number 2, I have a single carbon coming off of that? That's what this methyl group is. This methyl group is this group right here. Because meth is the prefix for 1 carbon, bute is the prefix for 4. And this is where it lives. This is its address. This doesn't tell me how many methyl groups I have. This 2 is telling me on the parent chain of 4. Butane is the parent chain. It gives the compound the last name. I have 4 carbons single bonded. Coming off carbon number 2, 1, 2, I have a methyl group. So that's where this name comes from. So all of these structures on this one page, they're all representing 2-methylbutane, the exact same compound. What I would like you to do is to get out your model kit, and I would like you to build this model. So go ahead and pause the video, build the model, come on back, and I'll talk to you some more. Okay, so take a look at your model. You'll notice you don't have a longer bond line here. That it's actually the same length as all the other carbon-carbon bonds. It's three-dimensional. This is flat on paper. So we don't always want to draw, when we draw the structure, we don't want to explicitly show the hydrogen. So what you want to do is when you draw this structure is you want to start with the first carbon, in this case on the left, and see how this carbon right here has 3 hydrogens. That's what this piece is right here. I'm telling you I have a carbon with 3 hydrogens on it. Sometimes, and you're going to be seeing this a lot more often, do you see how we have hydrogen first? Sometimes they'll put H3 on the left-hand side with a carbon and then go on to the rest of it. So this might sometimes have a hydrogen first and then the carbon. You'll be seeing these a lot again when we get to nomenclature, so you'll get a little more used to it. But what I want you to next see, okay, so we have 3 hydrogen with 3 carbons. What's next? My next carbon right here has 2 hydrogens. So it's always carbon and the number of hydrogens that follow it. This guy right here has 1 hydrogen. And did you notice I have this branch right here? This is the branch right here of the CH3. And then I made this line a little long, sorry about that. I have 1 more right here, CH3. So this is representing the structure above it. Let me go ahead and clean this up. All right, so I want you to go ahead and see that this does match this. It's condensed by putting all the hydrogens together. You don't have to show horizontal single bonds. It's understood that they are bonded together, but you must always show vertical bonds. Notice I had to still put in this bond here so I know that this is bonded here. Always go back and check that carbon has the appropriate number of bonds when you throw in your hydrogens. Carbon has to have 4 bonds. It has 3 to hydrogen and 1 to carbon, so that has 4. This carbon is bonded to this one, and it's also bonded to this one, so it only needs 2 hydrogens to get 4 bonds total, and you can also see it explicitly up here. This carbon has a bond to carbon, a second bond to another carbon, a third bond to another carbon, so it only needs 1 hydrogen. Again, here you could see what's happening. And then you have a CH3 group. You can also take, do you see how I have this carbon here? Let me highlight that one for you. This carbon here has 2 CH3 groups on it. That's the same as this carbon right here. So sometimes they'll make it even more condensed, and because this carbon has 2 CH3 groups, do you see how they put in parentheses 2 CH3 groups? You can even write it this way. So either of these are condensed structural formulas. Basically, anytime they ask for a structural formula, they mean condensed structural formula. It takes a lot of time to say condensed structural formula, so anytime they say structural formula, assume it's the condensed. Now, skeletal or line structures, these are pretty cool. what these are is anytime you have a bend or an end, you have a carbon there. And this is an intersection. I guess you could say intersection too, but this is also a bend. So you have a carbon here. So this is the same structure as the one before it. Take a look at this. I have a carbon here. There's one here. That would be the carbon on the end here. I have another carbon here. That would be this one here. I have another carbon here. That would be this guy here. I have another carbon here, and that's this guy here. And I have a fifth carbon here. Notice I have a total number of carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The line structure is really nice. The line structure you can draw it quickly. You can still get your point across on what you want. For this class, on the first exam, you're not allowed to use line structures. You must use condensed structural formulas, so I can make sure that you all know the appropriate number of hydrogens to fill in and that kind of stuff. And once, as a class as a whole, I pretty much geared that most of the students can go ahead and know how many hydrogens are appropriate. I'll start allowing skeletal structures. But the first exam for sure, you cannot write the answer to a question using the skeletal or line structure, but you'll have to know what that structure is. Again, you can't use the line structure as your answer. So one of the things that I've done in your class is there's a really good website, Compound Interest. It's called Compound Interest, but the website is www.compoundchem.com. And they have, it's an organic teacher, and he's made some really neat posters on a whole lot of information. And so every once in a while in your lecture notes, I'll be popping these up for you, and I'll give you the website if you want to take a closer look at it. But there's a really good brief guide to chemical formula. And so it shows you a great, what it does is a great version of what's the difference between a molecular formula, empirical, condensed. They call this displayed formula, or this is explicit formula, condensed, structural, and skeletal. So go ahead and pause the video if you want to take a closer look at this, or you can also visit the website. Earlier in this lecture, I asked you to go ahead and build a model of a compound. In fact, you should have your model kit out at all times, and a lot of times you might want to build a model even when I don't suggest it, so you can take a look at the molecules. It's almost impossible to learn how organic chemistry without a model kit, and so it's one of the #1 things you have to have for this class. We often need to visualize the shape or connections of a molecule in 3 dimensions, and that's what the model can do for us. Molecular models are 3-dimensional objects that represent the aspects of interest. Now, it's not going to be exact in necessarily the bond lengths and stuff like that, but it can still give us an idea. And there's also computer models are possible too, where they can have, they'll give you the model and you can rotate it 3D and all sorts of neat stuff like that. So let me describe the different kinds of models and model kits. So this is the model kit that I prefer you have for this class. There's a number of model kits, but this one is called a framework model, and it works extremely well with OCHEM, and it also helps us do some other properties later on. So carbon will have 4 holes pre-drilled in it, and hydrogen will only have 1. Oxygen will have 2. The sticks, we have a bond here with 2 electrons, showing you carbon is single bonded to this hydrogen, where carbon is double bonded to this oxygen here. And so they have these flexi sticks in there, and then here's another rigid stick. So those flexible sticks, reserve those for double or triple bonds. And then they have different bond lengths in that kit. I typically, they usually have the shorter ones. This kit comes with these little white, they're not even a bond. They look like a disc with little pieces on each end. That's typically what you would use between hydrogen and anything else. So you would, for example, use it here, but I don't like those at all because you have to use that tool that comes with it to remove them. So what I do is I go ahead and, just like they did here, is I go ahead and use this as my bond between these 2 here, and I understand that it's actually closer because those other ones are a pain to get out of there. And there's other, just knowing that it's close together is fine. So this is a model of this structure right here. This again is acetic acid. And I also showed you explicitly the hydrogens out here. So it's very similar here. And if you have your model kit, definitely put your model together during this part. So here's another type of model kit. I don't require you to have this one. This is called the space filling models. And there's also a lot of computer models that'll do this for you. This actually shows you more realistically where the electrons are being shared and what the actual shape of the molecule is. This is actually helps you see if there's crowding and that kind of stuff in a molecule here. So this is the one we're going to use for this class pretty much all the time, and I don't have these model kits for you, the space filling, but I'm sure you can see representatives of that online in computer models. So that's it for Exam Material 1, Part 2 video.